Okay, if you have ever seen an autonomous vehicle, you have definitely noticed that it has a big spinning contraption on its roof. This machine is called LiDAR, L-I-D-A-R, and it is one of the most basic sensors in every autonomous vehicle. In fact, it is a giant scanning laser that allows me to get a depth scan of the environment. And when I say depth, I mean that for each XY point in the plane, I have the distance or the depth from the LiDAR to the object. Before we start talking about the LiDAR, let's give some history. The LiDAR was invented back in the 60s along with the laser, and its first use was to measure cloud heights. You just point it out to the sky and measure the cloud height. The first awesome application was on the Apollo 15 space program, where the LiDAR was used to map the surface of the moon. You know, valleys, hills, aliens, etc. Today, the LiDAR is used on every autonomous vehicle, and there are several serious companies in the industry that develop it. As of filming this video, the leading company is called Velodyne. Now, if you are not dealing with big autonomous vehicles, you can run into another kind of LiDAR called RP LiDAR. LiDAR 1, RP LiDAR 2, and RP LiDAR 3, mainly used in universities and research labs. So how does the LiDAR work, and what is the physical principle behind it? The principle is what we call time of flight, TOF, which is basically a calculation of the time it takes for the signal to arrive. Now, in order to make or construct a LiDAR, all I need is a laser, a light sensor, and an extremely accurate watch. What I do is I send a laser beam from the LiDAR to the object. Now, the object can be another car, it can be a pedestrian, or even a wall barrier. The beam arrives, hits, and reflects in every direction. Some of it reflects in the opposite direction of the arrival. And that is what I pick up using my light sensor. I have an accurate stopwatch, and therefore I can measure the time elapsed since I sent the beam until I get it back. If I know the speed of light c, I know that t, the time, times c equals twice the distance from the LiDAR to the object. This is assuming that the object is stationary, which makes sense since the speed of light is approximately 300,000 kilometers per second, which is much faster than the relative speed of the object, the car, the vehicle, or even other objects. The methods explain how I get the distance from the LiDAR to one point in the plane. But what happens if I want the distance to every point in the plane? What I do is to take a mirror and spin it using a small motor. Now, I can measure the azimuth of the mirror, and from that, for each azimuth in the XY plane, I can get the distance. Now, if I want to expand it from a 2D plane to a 3D sphere, all I need to do is to add a little motor that changes the elevation. So basically, every point will have three parameters: range, distance, azimuth, and elevation. Using these three parameters in spherical coordinates, I can move or transfer them into Cartesian coordinates x, y, and z. The LiDAR gives us a lot of points, and the gathering of all the points in the space is called point cloud. The LiDAR gives us a lot of points in the space, and the gathering of all the points is called point cloud. What can we do with this point cloud? First, there is a wonderful library written in C++ which deals with this point cloud, and this library is called PCL, or Point Cloud Library. Now, we can do two things with this point cloud. First is reconstruction. You can reconstruct the environment from this point cloud. You can get a accurate 3D scan of the environment using this point cloud. And you can do it very accurately because modern LiDAR are extremely accurate. Another thing that you want to do is registration. What is registration? Let me explain. Let's assume that I'm at t equals 0 and I have some point cloud which capture a certain tree. What happens after 1 second at t equals 1? The car got closer to the tree. Maybe I even moved the wheel so I changed the orientation. Now I have a new set of points which represent the same tree. What we need to do is to register those two sets of points, meaning take a set of points measured at t0, which describes the tree, take another set of points at t equals 1, which describes the same tree from a different angle, and combine them, register between the two, and understand that the same set of points at t0 describes the same set or the same object at t equals 1. Unfortunately, in a minute, we are not going to cover this in this course. Why? Since we are not going to cover point clouds. Another thing that we need to remember is that from our perspective, what we get from the LiDAR is 2D position at X and position at Y. It is important to remember that we get it with respect to the vehicle position, not in global coordinates, just in relative coordinates. We assume that the vehicle is positioned at 0, 0 with orientation 0. We need to compute or extract the global coordinates from the relative coordinates. And lastly, I want to mention something that Elon Musk, the owner of Tesla, said a few years ago in a very big conference. He said the following thing.
And in cars, it's freaking stupid. It's expensive and unnecessary, and as Andre was saying, once you solve vision, it's worthless.
Why does Elon Musk think that LiDAR is stupid? Because we, as human beings, we don't navigate or get the depths using laser beams. We use our eyes, two eyes located in different positions that allows us to get a stereo vision. If I have two eyes or two cameras, I can get a sense of depth and even distance. So Elon Musk said basically the following thing. You can do exactly what humans do in autonomous cars. Just get two cameras from two different positions or two different angles and you can get the depths. Now, is Elon Musk right? I'm not here to judge. Let me just tell you that Elon Musk thinks that there is another sensor which is extremely important for self-driving cars. And this sensor is called radar. And we will discuss the radar in the next video.